All right. So today I want to try implement a hash table. Why is my drawing not working? What? Oh no. Okay, good. Okay. Today today I want to look at trying to implement a hash table, specifically where we're hashing unordered sets of IDs, right? So normally with hashing, you think of like you hash some kind of integer, right? Like from like the integers to some integer, and then that's cool. But today I want to do like sets of integers and map them to some number kind of thing, That's what this is today is all about. So I know basically nothing about hashing. Not nothing, but very, very little. And I especially know nothing about hashing sets of things, collections. So I started out by just doing some minor research, trying to figure out what might be suitable. So I asked Claude, you know, what's kind of the general, what's in the general literature? What can we maybe look into? And what it came up with was basically, especially if we're considering unordered, then the most important thing to understand is we're probably going to be using commutative operations. So things like XOR is probably going to show up a lot. If you want to naively just XOR all the elements together in a set, it works, but with lots of collisions. So you're likely to get different sets that give you the same hash key, and therefore the I guess hashing nature of the hash table isn't really being used properly. So the naive approach probably isn't going to be a good idea. And then it provided these two sort of other more the better ways of doing it. And there's this one which is like the first one, the polynomial one, where you hash each element individually and then XOR the result. Um, Maybe you can do some extra bit shifting and stuff to try and like make it a bit more random, I guess, or randomized. But the one that caught my eye because it has someone's last name in it is Zobrist hashing, which basically tries its best to, uh, I guess, hash a state. Now, yeah, originally it was for like board games like chess, where like for example in chess, how do you, I guess, compress the state of a game with all these different pieces on all these different squares. Zobrist hashing was kind of designed to do that problem. So each element in the universe, we'll talk about what that means, but each element in the universe is assigned a random, Claude says 64-bit integer. I'm assuming that's implementation based. Like I assume it's not necessarily 64-bit, but it was assigned some kind of random key at startup. So each element, and then the hash of a set, the hash of the thing we're trying to condense down with all these different elements, is the XOR of the random 64-bit integers that these elements correspond to. Because each element gets a random unique value, XOR cancellation is avoided in practice. Yeah, because like when you XOR like something with itself, XOR with itself, I think you get like 0, right? Because you'll get 0 if you XOR something with itself. So basically, because each element gets a unique value, that's not going to happen. You're not going to have a 0 output. And collisions are very unlikely, which is good. And my prompt involved talking about the regex stuff that I've been doing, so it mentions that stuff as well. So when it says each possible element in the universe, it means each element across all the sets that I likely will be hashing. So, let's say I've got like 3 sets that I want to hash, and the elements are like 4, 3, 7, 1, 2, 9, 8, 4, 11, then these elements are what will receive at the startup will receive a random 64-bit integer. So they will have like a number that is like a random key that they are associated with. Oh, and yeah, that's pretty much how that works. And yeah, so like the set's hash is equal to kind of, I guess, the XOR of each X in the set in the given the table. So like in the table, which is like, you know, each element and then the corresponding, you know, 64-bit key, you get all of these 64-bit keys for each element in the particular set that you're hashing, and you XOR those keys together. That's what's going on. So that's the idea. It also gave some resources because I asked, you know, if I wanted to do some further reading, but I ended up not doing any further reading besides looking at the Wikipedia article just to confirm that I knew what was going on. And then it kind of gave sort of a more practical suggestion, which was to sort the set so that the ordering was fixed, and then hash from there, like do a kind of sequential hashing, given that you know that the thing is sorted. So, but for the sake of lols, I want to try this thing. So what do I know? My kind of restrictions on my input is I have some upper bound for the universe's elements, like e.g. like if the upper bound was like 37, then the elements in the universe range from 0 through to 37. Like these are the only elements that I have to produce 64-bit keys for, is what I'm saying. Again, that's purely based, this constraint is based on my regex engine. So that's why I'm doing that. The side steps, that's fine, yeah, whatever. Yeah. And then I looked at the Wikipedia article. This is purely Wikipedia. This is not mine. I'm not trying to plagiarize. This is purely, you know, this is not mine. Okay. Yeah, and basically this goes through an example of when you're trying to hash a chessboard. I feel like this is meant to be somewhere over here, but I don't know where, unless it's like down here, but I'm just going to get rid of it because I don't know what it's for. I forgot what it's for. Okay, so yeah, for example, if you give each piece a number, white pawn, white rook, and black king, etc., 12, there's 12 unique pieces, 6 for white side, 6 for black side. Basically, yeah, for every square in the 8x8 board, and then for every piece, so for each pairwise square and piece, you generate a random bit string for that particular pair. And they also have this extra thing where they generate a bit string for if it's black's turn to move. And then, yeah, for when you want to hash an actual board, you iterate through the board squares, and every time you see a piece, you figure out exactly what key corresponds to that piece on that square, and you XOR, you know, the current hash number with that key, 64-bit key. And then, yeah, that's pretty much it. So yeah, just as we've already said this, but basically in this case, the elements in the universe is all of the pieces on each of these squares, basically. Each piece square pair is an element, as is whether it's black's turn to move or not. So Um, yeah. This has to change actually. I changed my mind about this. I'm going to be using uh, so yeah, my input is a sequence of integers, right? Making up the set of numbers, and then the hash key will be used to produce the index that the set that I'm hashing will be stored in. So the hash key being the thing that I'm zoring together, this final H thing, and the initialization. So for every possible element in my universe, that's what this basically is saying. For every possible element in my universe, we create the random 64-bit integer, like we said already, and we've got to keep those 64-bit integers safe and easily accessible. Then when we want to hash a particular set, for each element in the set, we need to extract, the 64-bit key that we stored up here, and then XOR all of those 64-bit keys together. We should then mod the result by the size of the hash table in order to make a valid index. This is like normal stuff. And then place the actual full-on set in that index. So the hash table itself, and yeah, there's some stuff about memory management, and I'll talk about that in a second. But structurally speaking, first we have the uh, element to 64-bit integer sort of table. So, for each element, we'll have, from 0 up to the upper bound, and correspondingly, there will be the 64-bit key. And the hash table itself is a bit more interesting because basically what we're going to do is the outer box over here is the overall hash table, right? With index 0, index 1, etc. And inside, each element of the hash table is going to be a set, the set that we're hashing. So this whole thing in here is going to be a set that we have hashed. And in terms of collision handling, I'm planning on doing, I was going to do chaining, but I think I might just do linear probing. Linear probing, normally you have to have like tombstone strategies and stuff in order, like whenever you want to delete an element, you have to do like certain things to make sure that you know when you've deleted an element or whatever. But I think in my use case, my very particular use case, I think I won't ever need to delete stuff. Like I'll never have to delete from the hash table. I will have to free everything eventually, but I don't think I'll ever have to delete. So I don't think I need to worry about tombstones in this case. So I think linear probing will be fine if I can remember how it works. And then, yeah, I just double checked I knew how to do this kind of thing. Generating 64-bit integers for those keys. Got the rand function, but that only gives 32 bits. So we got to do some bit shifting and got to need the particular libraries. What is this about? Oh yeah, sorry. Collisions, I mean about the keys between 64-bit keys. Because like if I've got to generate, let's say 100 keys for 100 elements, then I mean the chances of getting like the same number twice when you do this, when you run this line, is like quite low. So coding for that is like, I feel like going to be annoying. Not annoying, as in like annoying. Yeah, annoying. Not like difficult, but annoying. So for now, I'm just going to leave it and then I'll do it at the end. And then we'll do some seed stuff to try and make sure we get different numbers each time. And then the size of the hash table, generally you expect it to be a power of 2 or prime. And just as a guess, I'm thinking that 1024 might be a good size for the hash table. And something that I recalled due to Googling is that if you mod by a power of 2, right, because we're going to be modding in order to get a valid index, so after we get our key, we're going to be modding by the size. Modding by that size is the same thing as applying the AND operation on the size minus 1. And the reason for that, I kind of half proved it, like basically proved it, I think. It's a bit of a weird, it's not really a good proof, but it made sense. It validated it for me. In essence, what was the reason? When you mod by a power of 2, that power of 2 can be written as like, sorry, the thing that you're like on this side, the x value that you're modding by, can be written as like a series of bits. And when you consider the bottommost k bits and then everything else you expect to be divisible by 2 to the k, because it's like the sum of 2 to the k plus 1, or no, sorry, sum of 2 to the k plus 2 to the k plus 1 plus, like it's if you think about expanding that part out in binary, you expect that part to be divisible by 2 to the k. So when you work in mod of 2 to the k, that all that stuff reduces to 0 and you're left with just that stuff, the bottom k bits. And so the remainder, when you do this, you expect to be these bottom k bits. So what you want is to mask or to AND this guy with, 1, 1, 1, 1, 1 k times down the bottom, which you can do if you take 2 to the k and subtract 1. If you take 2 to the k and subtract 1, you will get a mask that looks like 1, 1, 1, 1, 1 k times, if you think about the binary, because 2 to the k itself is like 1 and then k zeros, right? So if you subtract 1, then you will be left with 0 and then 1, 1, 1, 1, 1, 1 with k ones. So, which is what we want. So anyway, it's not important. It's a typical trick. I forgot it, but then I re-remembered it up after Googling. So yeah, that's pretty much it. And now we are chilling. So I'm going to code, and it's kind of late, so I probably won't talk much, but we'll see. I have my water bottle, which is nice. Give another round. Um, while the thing. I think for now, assume resizing will not be necessary. So I'm not gonna have any resizing because resizing is gonna be annoying because I have to rehash everything, I think. But yeah. All right. Uh. Um. hmm. Um. Um. Upper bound plus one because it goes from 0 up to the upper bound, so there's one more element to care about. All right. So. Less than or equal to, we're going to table at I is equal to generate random key. And then yeah, so assuming no collisions occur. Because normally how you would check for a collision is you would use a hash table, wouldn't you? So it's a bit awkward. Anyway. So yeah, and then we can return, and then we can return the table, I guess. So we have that table. We have this guy done, kind of. And then maybe Zobrist. Do not put the variable name. Alright, so we have the space, and then Z. Generate table. So we got the key table. And then equals malloc size of, we'll say int star for now. It's a bunch of pointers pointing to the sets that we're going to be putting in. Size, we'll call it hash table size. Okay. So hang on, just note for myself, this should be private, this should be private, and then these two probably be public. So given the Zobrist, and given the set that we care about. Alright, here we go. Int set size. Maybe I'll make a struct for it. Or maybe I'll use the dynamic array, wouldn't I? Whoops, sorry. And then like, I need a type. So it's a set, so it stores a bunch of integers. And the label, it's called a set. Fine. What was that for again? Given a set. Should I say like you are a set thing, which means when I do this, it should be this. Make this up as well, might as well. So fair game. I have the random hash key, like the key table, and then I have an array of sets, which is what it is because yeah. Okay, should be good. And then what am I trying to do? For int I equals 0, I less than set. Maybe I'll just add the upper bound, just so I know what the upper bound was, you know? That way, like if int I equals 0, I less than s size, if the current element is bigger than the upper bound, then I think we should throw an error into standard error. Element in set larger than the Zobrist upper bound. So this is hashing Zobrist add, and then all right, and then exit one. Okay, just in case. I don't think that will happen for me, but it could. So if current element is greater than the upper bound, then yeah, throw a tantrum. Otherwise, I need to say an h zor equals, is that right? Zor, right? Zor equals z's key current element. Might also just put a size thing, just so that I have it. Okay. H. And what did I say? It's and the size cool. Can I wait? Do I have to calloc in order to make it definitely null? Do I have to be like calloc? Or sorry, should this be calloced? And then it's the number of elements and the size of each element. I don't really like callocing if I can help it, but I'm just worried because the way I'm going to check for gaps in the hash table is checking if it's null, so I think it has to be calloced. Or I have to malloc and then do a for loop anyway. So int index will have a private function. Or do I need to? find next available given start given the right, just given the next. And the idea is what have I done? Oh. All right, so we got the index that we want, and if if it fails, then we'll just exit out. God, such I'm gonna have a counter. Just for some logging, I'll do that, and then your HT, your data. Set pointers. Wait. It's an array of set, where set is in turn representing a dynamic array. Okay, that should be fine. Okay. Maybe I should call it capacity. That's fine, not that one. Okay. Num elements, is that better? Just to be really explicit. And then make sure you set that. And then over here, all right. And now I have to look it up. Oh God. So this will be private. And then this is all pointers, so I shouldn't have to return anything, right? Set should be mallet so that the scope stuff shouldn't kill it or anything. Should be fine, yeah. Alright, so sorry. Zobrist find given a Zobrist and given a set s. Alright. Alright, there should be a hash Zobrist hash. I spelled that very wrong. Zobrist hash given a Zobrist and given a set. Should I go so far as to get the index as well? Maybe not. I think that I like having the hash thing sort of separate. So all of you can go and we get Zobrist hash. Good. All right. Hopefully that works. Do I have to explicitly cast this? Is there going to be problems with like chopping off bits or something? Do I have to do that? We'll see. Zobrist hash. Yeah, right. And this can probably be private. You make the hash thingy, and then you get the number of elements in the set, and you go through each element, and you get the key thing. Cool. Okay. What did I do? find find nope. Start I less than Zobrist. What capacity? Can I just check that? When I for loop. Yeah, Zobrist capacity. Okay. And I'll say like int num misses, just so I can get an idea. For int I equals start, I less than Zobrist capacity plus plus I. If sets match between S and Zobrist HT data, then return I. Otherwise, num misses. If this guy is equal to null, yeah, because it's an array of sets. An array of sets, yeah. So if that should it be double pointer? A hash table is meant to be an array of pointers. A set itself is not a pointer, is it? I'm confused. Oh. Expression. Yeah, this doesn't make sense, right? Like I should be indexing. Yeah, wait, I tripped out. Hang on. One pointer means it's the. Yeah, I think double pointer makes sense. All right, should be good now. I think I need this as well. If either of them is null, then that's kind of crazy. Like, I don't think it should be. I'll put a warning. Hashing. Uh, okay. If S1 size is not the same as S2 size, then turn false. But if it's unordered, then this isn't going to work. Okay, so maybe these should be sorted. Maybe the sets need to be sorted. In which case, maybe this whole thing is pointless, but I'll still do it. Checking equality isn't going to make sense if not sorted, because like I basically would need a hash table. I would need a set structure already, which is kind of silly. Okay, we'll assume they're sorted. All right. I'll keep that in mind. I knew that as well. I thought about that before, but I forgot. If S1 data I is not the same as S2 data at I, return false. Why am I doing not more than one line? It's like, this is completely fine. So if the sets match, when you add an element to an already sorted set, to an already sorted thing, like a mostly sorted thing, when you add some random element, what's the worst case? Is it when you have like a really small element? Well, you can do it in linear time, right? Because you do a bunch of swaps until you find. Yeah, so you can sort in linear time every time you add an element to a set. So it's like an n squared thing, or it should be fine for this. Okay, that's fine. It's like it's not quadratic really. It's like the number of elements in the set multiplied by. Yeah, it's like an n squared thing. Which like this is small enough, it should be fine. All right, so start at start. Go through to the capacity. If it's equal to null, then don't check it. I mean, I don't think it ever will happen because like if the hash function got this start, then this particular set. Oh no, but the set might just not exist, right? The set might not exist. So yeah, if it's null, then yeah. Okay. If it's null, then it's a miss. If the sets match, then great. Otherwise, this is a miss. I'll print how many misses there were. And then for int I equals 0, I is less than start. And then this is very similar. It's exactly the same, actually. There's no way I can do this in one loop, right? Oh well. Wait, what? Okay, so we get the index, and then if we never return at this point, then we return -1. Nope. Find set. Start is index. If index is equal to -1, what am I meant to? What should I do? I think I just can just return false. Return index is not the same as -1. Like if I do this as boolean, because it's purely a set, I'm just checking if it's existing or not. Right? So I can just do it as a boolean thing. Like outside of this internal code, I shouldn't need to care about where the thing actually is. So what's the time? Oh god. Midnight. Alright, let's just quickly try test this. So I need to make a set called, I need to make sure that the set is always sorted, either by construction or something, but anyway. Okay, so let's make some sets and then go from there. Can I be like, 2, 3, 4, 5, 6, 7. Okay. Okay, so let's say we add 3 sets to the hash table. Oops. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. I wonder if I can use the addresses. Like, you know what I mean? Like, instead of storing the array, if I just store the address of the array, because obviously, no, that doesn't make sense actually. No, that's dumb. That's dumb. Sorry. Let me try Zobrist init, given the upper bound, which is so there's three sets I'm gonna put in. So I think I can put 3. Is that right? No. Upper bound refers to the actual. Oh god. Okay, maybe I shouldn't put 3,000. That's kind of dumb. 340, because the upper bound is determined by the maximum value within these elements. 340. Okay. So upper bound is, yeah, the upper bound is the biggest element. Okay. Whoops. That's all right. Zobrist. So you initialize it. Zobrist. What is it? Zobrist add, given Z and a particular set. Zobrist find. Did I spell it wrong? Oh, it exists. So Z S1. The thing is, if there is a complete cache miss, like if it doesn't find it at all, then does that mean maybe I do need the tombstone thing, don't I? Because yeah, if I hit a null, then to me that should mean that. Wait, yeah, I think okay, because right now if I hit a null, I just keep going and I just search the entire array, so it's basically a linear scan. So it's not really in the spirit of a hash table. So I think what I have to do is I need the tomb. Okay, I thought I could get away with not having the tombstone, but I think I will have to do that. So what would it be? It would be it would have to be like I need type def struct. Whoops. Type def struct. This would require the set. This would require the val. I don't even know what I want. This one will require the set array. No, single. And then an array of pointers to each Zobrist element, where a Zobrist element contains a set and also an indication of whether it's a tombstone or not. All right. All right, so stuff's gonna have to change. So you create the malloc for the overall Zobrist. You set the upper bound. You create the random key table. So it's a bunch of nulls originally. Or, yeah, it's callocked, but it's a bunch of nulls. So if it's a null, or if it's there but it's a tombstone set to true, that's how you know it's empty, quote unquote. If or Zobrist ht at I tombstone equals false. You know? So either if the element is null or it has stuff in it, but the tombstone is set to false. True, I mean, sorry. True. If it's null or it's dead, then you're allowed to use the spot. Okay, yeah. All right. So what is the idea when you come across a tombstone? That means you might have to keep going. But if you hit a null, then I think you can return. Uh, when you come across a tombstone, I think you might have to keep going because the idea is you might have added this set that you're looking for after this current set, and then you might have deleted this current set, which means there's a tombstone, and you have to keep looking past the tombstone to find the set you want. And then, but if you come across a straight up null, then it's like, if there was a null here, then your set should be here at this null. This set would have taken that null, definitely. So I think then instead of, you can say return -1 or return false even. I think I can make this a Boolean thing. Else if Zobrist ht tombstone, then num misses. Else if it's not dead and the sets match, if it's null, okay. And then yeah, I don't think I have to actually return the index. Okay. Just want to put some logging. If result else all right. Okay. Hmm. All right. Um. Whoops. Oh no. All my type changing has caused problems. Ah, of course, I didn't actually change the thing. I need to create a Zobrist element. So what is it? 135. Tombstone equals false. $171. Ah, I typed like 3 extra lines or something. Else if Zobrist. Okay. Right, that makes sense. Got to access the set, and we checked if it's null already, so that should be safe. Yeah, did that again. Sure. Okay. 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 That's good. And let me just try some of this stuff. Printf size of Zobrist. Okay. Okay. Cool. I mean that's terrible testing. I haven't actually checked anything really. Feeling a 1024 thing with filling a 1024 hash table with 3 elements obviously isn't going to test it much, but I don't think it's broken completely, which is good. Let me. All right, I'll go for another 10 minutes or 15 minutes. I just want to clean up the code because I wrote it poorly. I just wanted to get it right. I won't bother with header files and stuff yet, but I will. Okay, so I need to make a separate thing called set for sets. I want to make a. I want to make a structure for sets where insertion ensures that it stays sorted. Because I don't know, like unless I make another hash table structure, but it's like for integers, which should be simpler. Should be simpler, but I'll see if for my use case, I'll see if I can keep things sorted, just so I can take a shortcut. But I will eventually maybe make a set structure just for lols. Type def struct int upper bound number of elements in those for the Zobrist number of elements capacity, the key table, which is an array of 64-bit integers. Hash table is an array of Zobrist element pointers, where a Zobrist element is got a Boolean thing, and also it has a pointer that points to a set, where a set in turn is a dynamic array. Okay. A pointer to the dynamic array. A pointer to that struct. Okay, good, that makes sense. And I should probably make sure that the big things are put first. 8 bytes, 8 bytes, 4 byte, 4 byte, 4 byte. 8 bytes and 1 byte, surely. Okay, so this is, I back this. I back this. I need to free everything. Just to clarify as well, the reason why I'm happy is because these three exist. S1, S2, S3 should work because I appended those. I added those. So found makes sense. And then not found because S4 was never added. So, but if the other thing I want to try, actually, I forgot. The other thing I want to try was, what if I go S5 and make a completely new object? It shouldn't make a difference. I'm just curious. What? Oh shit, sorry. Why is it not? There we go. Did I break anything? Did I compile? Oh, I didn't do this. Sorry. I didn't check to see if it exists. Bang, found. S5 was found. So completely different object, but same elements. 211, 312 adds S3. So good stuff. Again, clear. Obviously, this is not sufficient testing, but I just wanted to make this is more for sanity checks. Nothing, blew up in my face. Just for reference. Whoa. Okay, cool. So that was fun. Do I want to read through anything? There was some really poorly written code. This is really bad. I think I'll do this first of all. Just have a separate case, and then if it's a tombstone, okay, I'll write it like this. If Zobrist ht what the heck hti tombstone, if it's not a tombstone and set matches, so if it's not a tombstone and then for the set to match, then do this, else none misses. Is this bad writing? I don't like it. Get rid of that. Hold up. Return true. Return false. Why would you return true there? Yeah, I'm annoyed that I copy and paste though. Surely I can do something about it. I guess I can make a second helper, but this is already a helper. Putting a helper in helper. I mean, whatever. I guess I can. Boolean. Is that more complicated to add a function there, or is it better? Because there is repetition, but it's just the for loop. What if I do it as a while loop? Then I can wrap it back around if I need to. While count is less than the Zobrist capacity, if I is equal to Zobrist capacity, I did put brackets, then I equals 0. Bring it back to 0 first. And then eventually I should increment and count should increment. Okay. So, and then you take this stuff. If you hit a proper null, then return false. If it's not a tombstone and the sets match, then happy days, we found it. Otherwise, the number of misses increases. And then increase I, which is the pointer that points to our current element. And then increase the count as well, because just so we keep track of how many elements we've touched. Once we've hit the full capacity, we know we've hit all the space in the hash table, and we have nothing else to do. So that way we don't need to do 2 for loops that look very similar. It's probably a way to write this as a for loop. I just don't know what it would be. Yeah, for count equals 0, count less than this, count plus plus, and then maybe that's better. For int count equals 0, count less than. And then you just have to also keep track of the I as well, that's all. If I is at the end, if it's invalid index, bring it up to 0. If it's a null, then it would have existed by now, so we can return false. If it's not a tombstone and it matches, then great. Otherwise, there's a miss. Okay, that's good. And I did something similar. Find next available. So yeah, similar deal. For int count equals 0, I count less than Zobrist. If I is equal to Zobrist, push I along, number of collisions also increases. This all goes. And yeah, if you never manage to find a valid index, int I equals 0, int count equals 0, count less than Zobrist capacity, count plus plus. If I is equal to Zobrist capacity, I equals 0. If it's null, is that right? Yes, if it's null or if it's a 2, yeah, yes, fine, sorry. then we found the empty place, we return I. Otherwise, number of collisions increases. Increase I. And if we eventually break out, it's because count reached Zobrist capacity, which means we touched everything. And for now, I'm not doing resizing, so I'm just killing it if that happens. Okay, that's pretty good. Okay, so do I like this? For int I equals 0, I less than size. For each thing in the set, current element equals s. So the only extra thing I would probably want to do is create, instead of sets being simple dynamic arrays, I want them to be have a bit more functionality, so that like they would basically be their own hash tables, so that I can easily check the comparison. I can easily compare two sets and check if they're equal to each other. Because right now I'm assuming that they're in order, which is why my tests are ascending order. But yeah. Oh, that's not good. Oh, I broke it. Oh dear. Okay. Number of collisions equals 0, 1, and 2. Interesting. Push. Alright. I'm too tired to figure this out. I'm gonna undo it. Back to the crappy for loops that were seemingly correct. I'll get at it and then push it across, and then I will. Oh, how far? Okay, so it's before this. Yep. Okay, yeah, that's for the last. Yeah, okay. Let me just check that. Okay, good. Okay, let me just. What's this called? Zobrist hashing. Wait, is my branch correct? Yeah, kind of. I haven't been branching correctly, but that's okay. Alright, now I can change my code as much as I want. Now I can break it as much as I want. Let's try that again. I don't know. I don't even know what I did, to be honest. For int count equals 0, count less than. I probably just like put the wrong variable or something. If I is equal to then bring it back to the start, and then from there run all this. If it's gone past the edge, reset it. If it's null, then we found a hole, return false. If it's not a tombstone and the sets match, return true. Else, we have an extra miss. And in fact, I don't need this, do I? because it returns in that if. All right, and then I back this mostly. Nope. And then if it's a hole or it's a tombstone, then by all means put it through. Get that index. Otherwise, collision and this one, which means I don't need any of this. All right, should be good. Well, I said that last time, but it's not a tombstone. Not a tombstone, yes. Not a tombstone. We can't be dead if we want to get the sets to match. Then return true. Otherwise, we had a miss, and we should increase the where the eye is pointing. So that should be good. Cool. And then I don't know what's happening. There we go. Okay, I don't know what I did last time, but I back it now. Slight clean. All right, we'll call it there. It's not bad. Just some nice little thing going.